everybody. Welcome back to another episode of our Coffee Breakdown podcast. We've been on a bit of a hiatus, so it's been about 2 years. And since then, Luca Violetto, who is the co-host of this podcast, has moved on to take an assistant professorship role at UCLA. And so we wish him good luck, but he will no longer be joining our podcast, which is unfortunate. But if there are people who want to do the low temperature plasmas and come on to the podcast to talk about their work, I'm very happy to still try and organize that. And you feel free to reach out. And aside from that, let's get on with our current recording. So today we have with us Pablo Rodriguez-Fernandez, who is a principal research scientist at MIT Plasma Science and Fusion Center. So welcome to the podcast, Pablo.
Thank you very much, Aaron. It's a pleasure to be here and welcome the new round for your podcast. Yeah,
Yeah, it's gonna be fun to try and take this on completely.
yeah.
It'll be a bit more relaxed schedule, but glad to have you on. So
Thank
Pablo,
you.
you work on plasma scenario optimization. You've worked on improving how we do these predictions with more modern computational techniques, including a bit of machine learning, surrogate modeling,
hmm
lots of very interesting work there. You've also made a name for yourself with the cold pulse modeling that you did previously, and we could touch on that later. But maybe to first
hmm
start off, could you explain a little bit about what is plasma scenario optimization in the terms of fusion and why it's important and why we want it?
Yeah, no, it's a great element to start with. So first, when talking about plasma scenario optimization, we have to talk about plasma scenario modeling, right? So what we're trying to do is to try to predict computationally. Well, we are trying to first understand, predict, and optimize the behavior of plasmas, right, inside these magnetic confinement fusion machines, right? So we have these tokamaks, these accelerators, these other confining methods, and we have this very hot ionized gas in the center, and we want to understand how it behaves so that we can get as much efficient fusion power and performance as we want, right? The fusion power really comes from the fusion reactions occurring in this plasma. So we have to control, predict, and optimize how hot this plasma gets, how dense, how robust, how stable it gets, right? So what we do in integrated modeling is to simulate that behavior, coupling different aspects of the plasma physics. So plasma physics and fusion is one of those areas where we have so many physics and engineering elements, right? We have electromagnetism, we have particle physics, kind of like kinetic theory, we have quantum mechanics, relativistic effects, we have some aspects of fluid mechanics. There are so many things going on in these plasmas that we need to have a comprehensive view of how it behaves when we act on it. That's where it comes, the idea of a scenario optimization, that in a machine, we have actuators, right? We have ways to act on the plasma. And those actuators can be from how we are heating the plasma, right? How many megawatts we're putting in, how we're putting those megawatts, how many particles we're putting through puffing of gas inside the chamber. What are the voltages and currents in the coils that are actually shaping the plasma? There's so many, let's say, engineering techniques that we have to make the plasma behave as we want it to behave. And when we are doing integrated modeling and scenario modeling, we are asking that question: how is the plasma reacting to those actuators that we have control over, right? Um, and the idea of optimization in a scenario modeling, a scenario optimization, comes from the fact that we want to find what are the best trajectories of those actuators such that the plasma is stable, is far from limits that we know make the plasma unstable, and that is producing the amount of fusion power and performance that we want, right? So it's a very coupled system of a lot of different modeling aspects, and at the same time high dimensional constraint dynamical optimization on top of it, right? So these are very complex um, very complex research topic, but it's one that is very, very important to tackle because, and comes to the second part of your question about why do we want scenario optimization? We want a scenario optimization because in future fusion devices, both burning plasmas like SPARC or ITER or fusion power plants in the future, we are not going to have as much experimental um, time, let's say, to do a lot of trial and error, which is how scenarios have been designed and operated in previous machines, right? We have experimental machines all around the world, a lot of tokamaks and accelerators, and research is about, well, running techniques, right? Running plasmas that you can measure how they behave when you act when you are acting on it, right? But in a device where you're not going to have that much computational time because it's very costly or because there are only a few facilities in the world that will be able to do it, then you have to use as much both experimental intuition of the physics operator that has that knowledge from previous experiments, but also the information that comes from this computational modeling. Let's use our best methods, our best models of how the plasma turbulence behaves, how the plasma heating behaves, how the boundary conditions of how the materials react to the plasma behave, such that we can make more conscious decisions about what are the experiments, what are the plasmas that we're going to create in those machines that will not damage the machine and that will produce the physics outputs that we want, right? Because in a machine like ITER and SPARC, that there are still experiments, we want to operate them in such a way that they will answer questions that will be important for future ones, for future power plants, right? So we want to say, okay, I want to run this experiment in such a way that is informing this open question that still exists in the community. And you want to use computational techniques to tell you how to run those discharges, how to create those plasmas in the most efficient way. So that's kind of summarizes a little bit what a scenario optimization is. And this is, as I was mentioning, a very high dimensional constraint optimization problem, a very difficult one, but is one that is required because sometimes, Aaron, and you're familiar with this because you work also on this topic, plasmas can become very nonlinear, right? The behavior of plasmas is very nonlinear, meaning that sometimes like small changes to some things can lead to very big changes afterwards, very big effects in some parameters, right? So we want to be able to control them with physics models that can reproduce those phenomena as best as we can. So that's kind of how I see it. It's also a way of mitigating and reducing the risk when we are thinking of running experiments in an expensive machine. We have to do that previous predict first planning of experiments if we want to succeed in fusion.
So that's actually a good point, and maybe you could expand a little bit on some of these, large changes that happen non-linearly in the plasma. I believe you've looked at a couple recently, where you notice that, oh, if we don't predict this well, we get massive changes, right? Like
Yeah,
not just changes in terms of, okay, the physics is slightly different, changes that affect like the engineering side, right? Like how much power the thing produces, right? And all this
yeah,
sort of stuff.
exactly. And yeah, and it's particularly important where you're thinking on about designing a new machine, right? So if you want a power plant that produces 1 gigawatt of thermal fusion power, you want to make sure that the scenario that is producing that gigawatt of fusion power is modeled with as high fidelity as we can, right? Because something that happens when you go to those burning plasma regimes, and for those that are not that familiar with that, what that means, when we start heating the plasma enough that it gets to a condition when it's producing a lot of fusion power, it also in a situation where it's self-heating itself, right? So we have out of the fusion reaction, and I'm talking here about DT fusion, right? There is the deuterium and tritium that fuse, they produce a neutron that you absorb and you heat water and move a turbine in the future with it, right? But there is also this alpha particle, this helium that remains in the plasma that hopefully, and that's one of the things that we need to check in these experiments in the future, will actually provide heat to the plasma itself, to the background plasma, meaning it reaches to a point where the plasma is giving itself energy to keep that high temperature. So you can actually uh, turn off kind of your auxiliary systems. You may not want to do that. You want to have some control over it, but it gets to a point where the plasma is producing a lot of the heat that it needs to sustain itself. And when you reach those burning conditions, small variations in how well the confined plasma is can lead to large excursions in how much fusion power is going to produce, right? And how hot it can get, right? So, um, what we have observed in simulations recently, a lot of the work that we're doing in the group is trying to understand what is the how does the uncertainty in the models that we use for those scenario optimization techniques, how do those uncertainties propagate to the final answer of how much fusion power my power plant will produce, right? And you realize that if you don't use high fidelity enough models with high enough fidelity, you may end up in situations where you are actually very far from your goal, right? Because it turns out that in a scenario modeling, integrated modeling, there is this hierarchy of different models that basically can be separated or like described in terms of the fidelity, the accuracy that they have, and the cost, the computational resources that are needed to run those type of simulations. Because sometimes you need to make simplifications to specific aspects of the physics, right? And if you make too many simplifications without the validation and verification that needs to come with it, you may end up in regimes that are actually not realistic when you start adding more physics into those models, right? So there is this idea that we can simply extrapolate from previous experiments. There is a quantity that we use in transport and confinement, which is the energy confinement time, right? That we have measured in many machines around the world. It describes how well the plasma energy is contained in these systems, right? And you can make extrapolations of your new machine that does not exist yet in this new regime will have this confinement time. And it turns out that if you're not careful and you don't model that new plasma regime properly with physics models, you may end up very, very far away from your goal of fusion power. And that's where physics modeling, scenario modeling, and optimization is super important for fusion endeavors, both private and public. We need to use as much information as we can from both experiment and computational techniques, physics modeling, fundamentals of how the plasmas behave if we want to build confidence in those regimes, in those designs.
Yeah, that's a very good point. And it also raises something else that maybe you've worked on or have ideas about is sort of because of these sensitivities where things can change so fast with like small variations in parameters, is there is the optimum just the best performance, or is it the plasma that has the widest operational space or stability
Yeah.
space, right? Like concepts of robust optimization, right? Are these
Yes.
things that factor in when you do the optimization? Are we there yet? Or maybe the simulations are too expensive, right? Like, what's your
Yeah.
thoughts there?
Yeah, no, that's a great question because one could say, well, the only thing that matters is fusion power, right? So I want to make my plasma pressure as high as possible because we know that fusion power goes as pressure square. Um, and in order to do that, you may just run very simple transport simulations and say, hey, if I build the machine with these parameters, I'm getting 3 gigawatts of thermal power, right? Of fusion power. But the real world is a very coupled physics and engineering system, right? Where you have to be careful in the types of regime that you are designing the reactor to operate at. You want a plasma that is not very disruptive, for example, right? So it turns out that if you, in the case of tokamaks, as an example, if you increase plasma current, a very interesting consequence in performance is that generally the performance increases. Suddenly the transport gets reduced and you get these higher pressures for the less input power. But it turns out that if you raise the plasma current too much, then the plasma starts behaving in an unstable way, right? And you may disrupt, and in a future power plant, fusion power plant, you cannot allow those disruptions to happen, right? So when doing the optimization, you have to not only care for fusion power, you have to care for stable plasma operation. And something very important is that sometimes, depending on the characteristics of your machine, you may not want to maximize fusion power because sometimes you may get to a situation where you get so much fusion power that you cannot extract it efficiently, right? So we know that in these reactions you are producing neutrons, right? Are your materials going to sustain that amount of neutron flux over long durations? Is the heat that eventually goes into the diverter, right? So in these tokamaks and accelerators, we have this hot confined plasma in the middle, but at some point the magnetic field lines are going to intersect a physical material, right? And the idea here is that you're going to try to make that intersection of the plasma with physical solid materials in such a way that you minimize the amount of flux, the amount of energy, the amount of power that is deposited in that material. And we have models or like we have techniques to simulate those phenomena. And that's where integrated modeling and scenario optimization is very important because then you have to couple all of that in a single system simulation and optimize it in a way that is either constrained optimization, right? You want to find the maximum input, the maximum output power out of your plasma while keeping the materials like that they last this amount of time, right? Or like they are not going to be damaged. You can see the system as a constraint optimization system or a multi-objective optimization system where you say, well, I'm going to, instead of finding just one optimal point, optimal scenario, I'm going to find this family of scenarios that are optimal in themselves. Like there is this idea of Pareto front, right? Where you're going to find what are the best solutions in this high dimensional space of objectives. And then you as a physics operator and you as a reactor tokamak designer, you're going to decide what is the risk or that I'm going to allow the machine to take, like that I'm allowing to take, right? So it becomes this very complex multi-objective optimization problem. And that's why in a scenario optimization, in a scenario modeling, we have to couple a lot of the physics that do not only end at the plasma, right? Sometimes we think of integrated modeling and scenario modeling as just modeling the plasma, right? With some boundary conditions. The real world is that that plasma needs to be coupled in the correct way with how the magnets work, how the blanket works, how the diverter works. You're going to be getting too high of a flux of impurities into your plasma because you're going to be eroding the walls, right? Are the neutrons going to damage too much the structures, and you're going to have to change the walls of the tokamak in just 1 year, or just a few months, right? There's a lot of coupled systems there that you cannot model them independently, right? Because there's a lot of nonlinear interactions in between them. There are a lot of feedback loops of if you go this route, then this different physics aspect is going to behave this other way, right? So you have to model everything at the same time, and that's why it's so complicated. It's a very multi-scale, multi-physics problem that couples the plasmas with engineering. Because and that's also actually what makes it also beautiful, right? I mean, it's such a complex physical problem. If you think about it, when we have these plasmas inside a machine, we have 100, 200 million degrees plasma, and 2 meters later, we have a magnet at a temperature of minus 250 degrees Celsius, something like that, right? So these huge gradients that is just a very interesting engineering and physics problem that we're trying to model all together and make it all work in an integrated way.
Yeah, that's super complicated, it seems. And that leads us to, I have kind of two questions as a, follow-up on this. Is like there's a lot of information density, right? So you have tons of models, tons of
Yeah,
variables, all these things you have to track across different domains as well, right? So each, you can look, just core plasma can take
yeah,
an entire lifetime of someone dedicated research to understand even a part of it, right? And then you are
Yeah.
crossing many domains in that manner. Um, what is the importance of let's say, the researcher expertise versus the models and learning how to run the models? How do you like? There's interconnections in terms of coupling models, but there's also interconnections in terms of coupling groups of people, right? So
Yeah.
how does this all work out in your head? Like someone who's really tried to do this from like a holistic point of view. What are your opinions?
Yeah, I mean, this is a great question. Something that I think generally in the community, in the fusion, plasma physics, tokamak designer community, we're trying to learn how to do that, right? Because for many years it has been very isolated. There has been the work in turbulence and transport for the core, work in the edge of how to exhaust the heat near the diverter. There has been work in the blankets, right? In how to breathe tritium. And now it's getting to a point where we are getting close to having an integrated system that needs to have all of that at the same time, right? So it is actually now when we are starting to encounter those synergies in between the different researches and groups. And there is this whole like initiative all around the world in basically every device, every group of core edge integration as an example of this, right? You have to find solutions that are not only good for the core of the plasma, right? That is not only high performance core is what matters, right? You have to find a high performance core that also makes the diverter and edge of the plasma survive, right? And there is a lot of very complicated interactions there, right? Because it turns out that as you make the plasma core higher performing, the edge solution becomes harder. And when the edge solution becomes easier, meaning when you are radiating a lot of power because you're putting impurities, that damages the core performance, right? So this has been for many years kind of like a fight in between, or a fight. What I'm saying is like different perspectives of the work of core and edge modelers. And now I think all around the world there is this idea that we have to bring the two of them together. And when we are doing modeling of a plasma scenario in an upcoming machine like SPARC or ITER, or designing a new machine like Demo and ARC, we are for the first time, I believe, we are trying to do a good job in connecting the two things and not just optimizing for one of them. And that comes from the fact that in experiments all around the world, having a like you are able to do a lot of experimentation. That's why they are experiments, and there are a lot of trial and error, and you are able to isolate better the different components. But you're not going to be able to do that in a future experiment, in a future machine like ITER or Spark. You're not going to be able to run a high performance core if the edge doesn't survive. Like you cannot do that, right? So I think this is something that we are as a community learning. And this becomes a problem also of the choice of accurate models to do that, right? Because if we were able today to take the full physics that's going on in the core and the full physics that's going on at the edge, and we couple it together, we have an answer. We can use that big simulation to optimize against. But we don't have that, right? And the reason why we don't have that is because it becomes very expensive. It is this very multi-scale, multi-variable, high-dimensional system that you had to make some choices of what is the accuracy of the different elements of the physics that you want to simulate, right? And I give you an example of something like that that happens in core turbulent transport. When we try to model that, we make the choice of, well, in the regimes that we're looking for future devices, we're going to ignore the short scales of electron gyro motion in this turbulence, right? We're going to only look into ion scale, like long wavelength type of like turbulent structures, because we have studied that we have determined that that is what really is important to model for to have an accurate description of turbulence in future devices, right? So you make choices that simplify the models in such a way that you're not losing accuracy, right? And doing that is extremely difficult problem. We can do that in some situations, but in some other situations, plasma physics is not that good in the sense of like, yeah, you may actually need to do this in a multi-scale way if you want to have a reliable answer in a nonlinear way. So this has been a big problem, particularly when trying to couple core and edge, because there is this multi-scale problem. And when you approach the edge of the plasma, you then end up with having to revisit some of the assumptions that you were using in the core modeling, right? So there is this very difficult problem of trying to find the right fidelity and of the models while keeping the computational cost, the computational resources at a reasonable level, right? So this is, I'm giving you this example between core edge integration because I think it's one that exemplifies what we're trying to say here. But this happens with also every other system, right? I mean, we're trying to also model the erosion and sputtering of materials, or we're trying to model the neutron flux that then is used to look into the neutronics and how neutron transport happens in the structures of the materials, the structural materials, or even the tritium blanket. Like there's a lot of physics there that I don't think ever we have had a comprehensive system that models all of that at the same time. And we're going to need that if we want a reliable, robust fusion reactor.
Yeah, that's a extremely good point. And as you know, I've also done work and trying to figure out how these different things might combine together. But
Yeah.
there's a lot of models out there that are too computationally expensive to just sort of couple directly, right? And
Yes.
there was a second question to the earlier point, but we'll put that aside for now because I think this is a great tangent. Um,
Okay.
which is kind of going into, well, like, what can we do about that, right? Because when we have these extremely, extremely complicated models, I suppose in the past people have done reduced order versions of these
Yep.
models, like in turbulence, where we do the quasi-linear assumption and the big quasi-linear models. Is that a viable process to approach all the other domains as well? Or is there something else? Maybe you've done work with surrogate modeling,
Yeah.
right? Like, does that work better? What do you
Yeah.
have to say there?
No, that's a great question. And yeah, I think the idea of trying to find surrogate models that try to reproduce the actual realistic physics that's going on in a more computationally efficient way is key to all of these, right? Because as I was saying, we cannot afford running a full physics, to take the kinetic equation for the distribution function of every species and you couple it with Maxwell's equation and you're done in the plasma, right? You can do that. But we start adding assumptions to that. And when I say surrogate modeling, I think the word surrogate modeling can be applied to both reduced physics modeling and also machine learning models. And we can talk about that in a little bit. Because what we are trying to do something like when we're trying to talk about or like to do surrogate modeling, what we are trying to do is to, as we're saying, having a substitution, a surrogate of the full physics model. And that could be by reducing the physics, right? As you mentioned, quasi-linear assumption for turbulence, stuff like that. Or now in the last few years, we have seen this rise of machine learning and artificial intelligence, right? Where maybe you are not doing a reduction of the physics accuracy of your equations, but instead what you're trying to do is, well, I'm gonna have this offline training of a surrogate machine learning model that maybe I can afford running thousands of millions of simulations offline, but I just do it once. And then I end up with a model that is either analytical or very fast to evaluate, like a neural network, transformer, this type of surrogate models that appears from the machine learning community. And then you can if you trust, and we can further discuss this, but if you then trust that the surrogate model, this machine learning model, is capturing the right physics, that is capturing this mapping between inputs and outputs of every specific element of the physics, then you can then couple that to to have this integrated scenario modeling suite that you wish, right? So you could have a surrogate model, machine learning model of core transport and turbulence, one for the edge, one for the materials, one for etc. And it brings us to this idea that some people in the community has been talking about of like having a digital twin of the machine, right? And the only way to have a digital twin of the machine really because of all these multi-scale nonlinear problems is to actually have reduced models or surrogate models, machine learning models out of the different components. And there is a benefit of trying to construct surrogate models out of smaller physics pieces, right? Because it's very different if you want to, for example, say, have this comprehensive simulation of my reactor that takes as inputs the actuators that I was talking earlier, like heating and fueling and coil currents, and it outputs fusion power and how far you are from stability boundaries. In principle, you could say, well, I'm going to just run many of those simulations and train a surrogate model of that output variable with my inputs.
Mhm.
That is going to be extremely complicated, right? Because there's so many nonlinear interactions happening in that simulation that doing it in a direct way can become very expensive. The training of that is going to be very, very expensive. And the surrogate models, these kind of like analytical, if you wish, mathematical representations are going to be very complex. Um, a smarter idea is, and that's what the community is working on, is trying to find surrogate models of specific physics components and using a physics informed coupling of those surrogates, right? We know how the core and edge talk to each other, right? They do it through boundary conditions. They do it through power fluxes that cross the boundary between the two. The same way as the neutronics, it receives the neutrons out of the core, right? We know the physics links in between those elements, right? So if you build surrogate models of the smaller pieces, it becomes, in my opinion, an easier full model to train on, right? So that's what I think in the community we're pushing for is like let's add as much physics guidance as we can when we are doing those machine learning models. So for example, in my work, I work specifically in the last few years. I've been working on this coupling of turbulence codes with macroscopic transport codes, right? So that's a very multi-scale problem because turbulence scales in the plasma are very small and very fast, but the transport, like how the kinetic profiles, the temperature and density behave, they do in a much longer time scales and much larger spatial scales. So in order to have a full simulation of the entire thing, you try to couple it in a smarter way. You say, well, I know that turbulence because it happens much faster than the transport timescales, I can consider the background profiles to be fixed. And then you run surrogate models of just this background, this turbulence system with constant background. And once you have the surrogate model, you can couple it to the macroscopic plasma evolution. And doing it that way, you end up with needing less training data, which basically translates in computational cost of how you're fitting the model. And it makes the physics as well more interpretable, right? Because one of the problems with surrogate modeling is that in many situations we're talking about black box models, right? It's like it gives you give inputs, it gives you an output, and are you going to trust that you're going to run that scenario in your machine if you don't know exactly why it got to that solution? So when you divide the problem in smaller components, it becomes more interpretable of why the simulation, why the AI system, if you're using that, is suggesting that you should run these charts to optimize the performance, right? So yeah,
Yeah, no, I mean, I would like to throw forward, let's say, a challenge on that, just to think about, right? Not because
yes,
I feel it's a problem. But is there a risk that if you have a system with many, many moving parts, small components trained or developed by different people for different, let's say parts of parameter space, that when you put it all together, it's just highly unstable. It can never find a solution, right? Is there a risk that by not doing it as a true holistic model from the start, that you end up with a
yeah.
ton of numerical instabilities at the end?
Well, but if it gets to that point, Aaron, then that's a way for you to then go and see why that happened, right? Because what could happen is well, I'm going to train my core transport model in this parameter regime, my edge transport model in this parameter regime, and I'm going to couple it together. And suddenly, as you say, it becomes unstable and numerically it doesn't get to a solution. The question is, well, maybe it's because during the trajectory in this scenario optimization technique, it got to a regime where you didn't train the originally the core transport model, right? Or it's getting to a situation where the dynamics are not physically constrained, right? It's not following thermodynamics, or it's not, it's just giving you nonsensical results, right? So I think it is true that it's challenging to do it that way, but I think it's the safest way to get to the answer, right? It provides a method for you to go and see what is missing in the surrogate model to make it more accurate. That's my feeling. Because if you try to fit the entire system instead of just smaller pieces, I think it would become even harder if suddenly it becomes numerically unstable and it gets to a regime that it doesn't make sense. Because then you cannot poke and say, okay, why did that happen? And it's like, oh well, the core transport model that entered in the couple system was never run during this big training data set in this parameter regime, but you don't have that information if you are actually fitting the entire system. So that's why I do think there is a benefit of doing element by element and trying to get insights of why it failed, right? So, and this actually brings to the important point of I don't think we should be fitting a model and having this holistic simulation and just trust it and run the machine or design a machine on, right? I think these methods provide a way to scope the parameter space, but then we should be doing validation and verification of those answers, right? That's my opinion. For example, and that's what we do when we design future devices. We're not taking nonlinear gyrokinetic profile predictions and use that to optimize a future power plant. No, what we are doing is to take the simplest model, empirical models first, see how the parameter space looks like, see, oh, maybe this region of magnetic field and size makes sense. Let's now use medium fidelity models, something like quasi-linear turbulent models, and try to have a more physics guided view of that parameter space. And maybe you realize, hey, from that space that empirical models told me I should be looking at, really only this corner matters. Then you only look into that corner, identify interesting points, and then you run the more expensive nonlinear gyrokinetic simulation, right? I think there is the hierarchy of let's use surrogate models, these holistic coupled models, not as a final product, but as a way to get you there faster. And of course, once we have a fusion reactor working in a power plant, we're not going to be running different scenarios. We're going to be running one scenario all the time, right? When we get to that situation and we have models truly trained on that parameter regime, and we ensure that it's numerically stable, that we ensure it works, then is when we can trust it, right? But at the moment, when we are first doing very broad, wide parameter space design optimization or plasma scenario experiment optimization, we should be going back to the physics, right? And see why they failed and how to improve it, right? So that's the way I see it. I don't know if that challenged back what you said, but I think it's an important point to reconsider. Yeah,
No, I think no, it's a solid rebuttal, and which I agree with at the
yeah,
end of the day, right? We really should be
yeah,
doing verification and validation of all our models, slowly, of course, because this is a complicated procedure,
yeah.
getting experimental data and all this sort of stuff, um, to kind of prove that what we've modeled or simulated is close enough to reality that we can trust it for these exercises, these optimization
Exactly. Yeah,
exercises.
there
Yeah.
is. It's super important. I mean, right now we're around the world doing all these reactor design studies, right? Because we are getting close to having something that is integrated. But there is this huge role that experimental facilities still have, both current ones and the ones that we're going to be building as a stepping stone to a reactor, right? SPARC either. But I'm also talking about current machines where we're doing validation of those models, right? It is true that in some situations the plasma regimes in future devices are going to be different, right? So there's going to be always a level of extrapolation, and that's why we are building new ones that are going to be approaching those reactor conditions, but doing this constant like prediction, experimentation, validation, improvement cycle is the way we should be doing things.
Yeah, and I agree completely there. I think that one of the, well, this comes back down to like model fidelity at the end of the day,
Yeah,
right? So because these validation exercises, of course, should be done with the highest fidelity model, but in practice, if you want to really take advantage of experimental data being produced, daily at a machine or something like that. They have to kind of be fast enough that you can check everything, right? Because if
yeah,
you only check the one discharge or the one experiment where everybody says
yeah,
this was the best, maybe you're
yes,
missing information. And so there is
exactly. And
there's a
yeah,
trade-off there, right? Like how fast can you run your model where you still trust the output and then can say that the experiment and the model match versus how many like how high fidelity do you need for them to even match in the first place, right? So yeah,
yeah. It's very important to have this idea. I mean, this hierarchy that I was talking about when thinking about designing a machine of first going low fidelity to scope the space and move forward. I think in the validation endeavor, we should also be applying that, right? Out of these existing machines, there's so much data and so many scenarios coming that you cannot run turbulent nonlinear kinetic simulations in all of them. But an approach could be, well, I have surrogate models out of the quasi-linear ones, right? TGLF, quali-keys, those surrogate models, those machine learning models. Let's see where they fail because you can run them very fast in every single shot. I think that's something that we should be doing more. And we can determine in which situations they are very far away and when they're not, and start going this next level of the hierarchy and then run profile predictions or scenario simulations with the full quasi-linear model. And if they agree, but the neural network didn't, then you have to go back and say, oh, okay, maybe it was outside of the training range. Maybe we should be sampling the that space, sampling the high dimensional space better in this region or not, because there's this transition in this mode that happened. And if it doesn't match, then you go the next hierarchy level and say, okay, why does the quasi-linear assumption fail in this plasma? Now you go and run your turbulence simulation and say, oh, wow, it's because we are in this transition between ITG and TM modes where there's this mixed mode behavior that is very poorly captured by just the linear physics with the saturation rule for turbulence, right? I mean, that's just giving examples. But I do think that there is a value of still doing that hierarchy of physics in the validation process as well, not only the design of machines. Yeah,
yeah,
and I think I think we should be doing it more. I think this should be it should be more accessible to do that type of big data study, right?
yeah,
Particularly in the existing machines, because there's so much data that has been generated for years of high quality data in a lot of tokamaks in very different parameter spaces. The problem, and you're very familiar with this, is that the data is not always as available as it sounds like. It comes out of the experiment, but then you have to, of course, have diagnosticians check that data, interpret it, fit profiles, and get the quantities that then are useful for the machine learning validation exercise, right? So I do think that there is a huge value in trying to do that in a more systematic, consistent way. And I know that there are efforts around the world going in that direction because that's the way we should be going.
yeah, and I agree with that, of course, completely, and that's also part of the work I'm doing, right? Trying to
Yeah,
build these workflows or at least build these connections that we can start having experimental data flow a little bit better around,
yeah,
and we can really check these things. But of course, this kind of comes back, and I would like to pose a question to you on this that we can agree that this is necessary to have these, workflows going all the time. Some semblance of them already exist in machines. They have their, intershot. analysis routine
Yeah,
that kind of goes, it's not at the fidelity that we as the physicists normally want, but they have something there. And so it's not like it's completely impossible, but it's clear that if it were simple enough to do and approachable enough that more machines or more parts of the community would have already embraced it. And so, what is your opinion?
yeah,
How do we get it there, right? Like, how would you try to push it towards that goal, which is really kind of what a digital twin is
yeah,
supposed to do anyway, right?
yeah. Yeah, no, that's a great question. And I think to enable more systematic validation of these big models, I think we have to make that validation process more robust to uncertainties, or how high can we go in the or like how low we can go in the hierarchy of post-processing of experimental data. Like, can we get to a point where we can take the raw signals out of the diagnostics in a machine and already do validation with that? Or like, can we actually build workflows that automatically triage those signals and produce something that can be used in the workflows? So I think the way I would approach it is try to go a little bit also the big data route of not worry too much about whether these plasma discharge, these plasma shots, the quality of your ion temperature data is perfect at every time step. Is more of like, okay, can we look at the statistics of a lot of shots? And even if the data has high error bars because it has not been processed by a human exactly looking into all the details of the line radiation fits and all that stuff, um, if we are able to create workflows that are robust to those uncertainties, that are robust to not having that data as prepared and having like blanks, gaps in the data, that's very important, right? Imagine a situation where you run a machine and you didn't turn on the measurement of ion temperature, which is something very common, right? Because ion temperature turns out is very hard to measure, right? So not every machine has it in every experiment. However, it's super important to validate our models, as you know, because ion temperature is what gives you fusion power and what gives you the main turbulence stability. But can we find ways to fill these gaps with as much information maybe from other diagnostics or information from physics that we know is more robust than what we are trying to validate? For example, we know that maybe it's more robust to have the physics of collision coupling between electrons and ions and the resistivity and the collision rates. It's more robust than the turbulent transport modeling that we're trying to validate, right? So can we actually use that physics that we're trying to assume it has and use it to fill that gap of the ion temperature, right? As an example, right? So I think that's the way I would go. I don't know exactly how to implement it in every machine, but I do think that being more robust to sparse data is very important in those validation workflows.
Yeah, that's going to be a whole, discussion on data
Yeah,
techniques and stuff. Like,
I know.
how do we ensure that we have accurate models in sparse environment, like data poor environments?
Yeah,
Which of course I'm very interested in. I know there are many people who are trying to do this as well around the world in fusion.
yeah.
So it's a good point that going the route of statistical data analysis where we have a
Hmm.
large pool of data and we don't worry too much about like does this match this one point, right? But as a
Yes.
as an aggregate whole, are we like
Yeah,
60% accurate? Are we 80% accurate? Like that would be really
exactly.
nice,
And
right?
and and for that example that you just gave, I mean, that one single point where it did pretty poorly, maybe eventually leads to further studies of why, right? And maybe you go in deeper into that and say, well, it's actually because the diagnostic data was very, very bad in that machine. We cannot do much about validation there. Or maybe it's because you suddenly hit an interesting instability in the plasma, right? Maybe become too electromagnetic and suddenly you have these KBMs in the core, or something that is making that point be kind of an outlier for that specific machine, things like that, right? So I do think, so what we were saying, looking into it with a statistical mindset, but also the physics mindset of like, okay, that outlier looks interesting. Let's look at the physics of it. I think combination of those two things is very important.
Yeah, that I agree completely, and I think that this is the point of like the large scale
Yeah.
data validation and stuff that many people are looking at. I think that
Yeah.
if we can develop the techniques to not only make the simulations not necessarily faster, but like routinely run, right? That
Yes.
they are routinely they just kind of data scrape if we have access and run everything, and then intelligent ways to pick out those outliers because it's a ton of data that gets produced, right, from these
Yeah.
simulations. And so like build in from expert knowledge where they look for problems and
Yes.
use
Yeah.
those to flag like okay this one's not that close to the experimental data, and then we check all those things and just kind of flag it and say like oh
Yeah.
that one might be wrong because of this, and then experts
And
can look at it, right?
exactly. And if you do that in a systematic way, intershot or like very fast, then you can actually use that information to tell you where to run next, right? Because if you identify with this statistical technique a region of the parameter space where things are failing in a lot of the models, that's where maybe you should be running the experiment next and explore that farther, right? I mean, we have to remember that the facilities that we have today and that we will have tomorrow, like in 5, 10 years, are still going to be experimental facilities where we should be doing a lot of this validation work and finding solutions, right? So I do think I do have the physicist mindset of actually where things don't work, that's the interesting regime, right?
Yeah.
And that's where we should poke. Yeah.
And this kind of comes back around to the second branch question that I had, which we left on
Yeah.
the
Which one
side.
was that?
Yeah, so this question is gonna be like, um, so you've worked on the SPARC, scenario development, which was a great hit, and also are continuing work with CFS through MIT on whatever they need.
Mhm.
How is the discussion around risk? Like, what do you find is an appropriate way to tackle risk? As you said, like from a physicist point of view, when it doesn't work, that's when we're interested. But
Yeah.
maybe from a different point of view, they are when it doesn't work is when they want to avoid it, right?
Yes, no, no, that's a great point. Particularly when you're building a very expensive facility and you don't want to break it. You want to, have a core that produces Q of 5, Q of 10, but that's not melt a diverter, right? So
Right.
so there's a lot of constraints there. And the conversations go and the work goes in the direction of quantifying uncertainty. Because if you're able to quantify the uncertainty in those predictions in a sensible way, then you can make choices of how much risk you're willing to take. I mean, fusion is a high risk, high reward thing, right? And when we are building a machine, there is a level of risk that you're happy um, to assume because the reward can be very big, right? So the way we do it in modeling is, well, let's be aware of the things that we don't know and try to um, characterize the uncertainty and how it propagates to the final answer, right? So, for example, if, as I was telling you, that the edge physics, it's very complicated to simulate, right? And we don't have yet a comprehensive model that describes the full edge physics of a tokamak. But we do have models, and we have both experimental data from previous devices that we can use for extrapolations, but also some reduced models that can tell us a little bit about what are the expected pressures that you're going to get as towards the edge, right? And then you can evaluate what is the uncertainty of that choice? And you can evaluate that uncertainty in a way, for example, looking again, going back to the big data idea, let's look at how that reduced model that you're using or that scaling law that you're using, how it behaves in current machines. What is the error that it has on that training data, right? And then you can maybe be a little bit more optimistic or pessimistic and say, well, when we're extrapolating to the regime, we may have a little bit more uncertainty because we haven't run machines with these parameters, right? And then you take that uncertainty that you have estimated and determined and propagate it through your model and say, well, it turns out that the boundary condition, a 20% change in the boundary condition has a factor of two change in the fusion power and stuff like that, right? So the idea is to get distributions of what is the both the most probable fusion power or like performance that you're going to get, but also how robust you are. And that comes to the second part of your question. You're talking about robust optimization, right? You don't want to be designing a machine where, okay, the probability of reaching your goal is very high, but if you go a tiny bit outside of that, now you are very, very out, very away from your target, right? You want to design a machine, an experiment where you have these very broad distributions where maybe you do not hit a fusion gain of 10 with the highest probability, but you say, well, the probability of reaching Q greater than 5 or Q greater than 2, Q greater than 1 is very high, right? And then you can take that information and say, well, let's aim for that. Let's try to kind of collapse that distribution as data comes in, right? You may say, well, I'm going to design it to run in this regime where we are predicting to have this high probability of success, and you define success with different metrics. Then you run the experiment, and once the data comes, it's like, okay, now my assumption that I made, we need to correct it, and or we have to collapse it in this way, and now my distribution changes, right? So you start doing that iteration process as data starts arriving from the experiment so that the next shot, the next campaign, the next year of operation, now you have more knowledge about how to make it better, right? How to make it more robust and get to the final answer. So I do think that, yeah, there is this huge role of characterizing uncertainty and doing the optimization, accounting for robustness of your design point. That's very, very important. You don't want to be in this very narrow parameter space that so your models predict success, but because they're uncertain, you may actually drop out of that. There's this huge hell that suddenly you don't get the fusion power that you want, right?
Yeah, and I think it's important to like even as somebody who's like doing the physics and running the models to keep an open mind on like different optimizations. Like when something comes out of the algorithm and you're like, I don't know if I agree with that that situation.
Yeah,
It might still be worth pushing it forward and exploring it because it may be better for other things, right? I think that kind of, I would say I'm in a privileged position when you're talking about integrated models because it's integrated, meaning you get insights from many different components all at once rather than one specific domain, and you can kind of see it all come together. But that coming with that privilege is sort of the difficulty of
yes,
understanding where the trade-offs are and making that kind of judgment call,
yeah,
which is never easy, but like that's part of
yeah.
the optimization as well, right?
I that's why I do think that the teams need to be very multidisciplinary, right? I
Mm,
don't think we are at a point where you create a surrogate model for this specific physics and you just put it online open source for other people to use and they forget about where it came from and all that stuff, right? I do think that the teams need to have all these physics knowledge and expertise in them so that the solutions that they find make sense from the physics standpoint and not just because your digital twin told you to do that, right?
right.
So you have to go back in history, let's say, and look at how that data was created for that surrogate model. What are the estimated uncertainties and the regimes that it should be applied on, right?
Yeah, and that's a very good point to end this. So we're kind of reaching on our hour. Um, the physics is important, and we should always keep it in
Yes.
mind. I think that that is the a great final message to end on. I'd like to thank you again, Pablo, for joining. It's a great conversation. We could continue this another
We could,
hour,
yes.
2 hours. It's just so much in my
Yeah.
interest and your interest, domain of interest, as well. So, but for the sake of everybody out there, I hope they've gotten a taste of what it's like to do plasma scenario optimization and all the different variables we have to play with, and how rich the field is for discovering new things and seeing really what happens inside the fusion plasma. So thank you again, Pablo, for joining us, and maybe we'll have you on again another day when you
Yeah.
have exciting news to share.
Great. Thank you very much, Aaron. It was a great conversation. I really enjoyed it.